Andrew already told everything, so it's my master thesis final presentation. And I'm gonna tell you about a Martian ice miner to support a colony on Mars. So I'll quickly go through what we'll talk about. So introducing everything, goals, what I wanted to do, where to find water on Mars and how to extract it, then the mining system itself and its most important subsystems, what needs to be around the miner for it to work, what technology we still need and what we already have for this to work, and final conclusions. So the next logical step in human space flight would be to send humans to Mars. Why to Mars? Because there is water, there is an atmosphere, and it's possible that there was life, maybe life even came from Mars on Earth. Now, it takes a long time to go to Mars, from 6 months to a year, and the way the launch opportunities are distributed, this is given by the orbital geometry. There is only very short stays allowed if you directly want to go back. That's why permanent stays, or at least until the next launch window, which is 2 years later, are put forward. It costs a lot to bring weight to Mars, which is why you want to minimize the weight you actually send there. And a way to do so is to use resources that are present on Mars. The most important for humans to live is water. And from water we can derive oxygen, which is almost equally important. And there is water on Mars, and if we use that, we can minimize the weight we send there and reduce costs. NASA plans to do this. By 2030, they stated they want to have humans on Mars, and they developed the technology that is needed to do so with the Orion capsule and SLS, for example. So the goals of my thesis was to identify the water requirement for a Martian colony, to identify a water mining method, to identify and size the machinery that is needed to extract water and its subsystems, show technical feasibility, and find performance like mining rate, weight, technical maturity, and technology. The water requirement was stated to be of 30 liters for a crew of 4. This is mainly for watering the food growing plants, and to a little part also for drinking and other human needs, let's say, that include water. So also part of the approach was to locate the water on Mars, which I will talk about now. The way water is identified on Mars is, for one, there is an orbiting spacecraft called Mars Odyssey, which has a gamma ray spectrometer, and this spectrometer detects hydrogen, and you can see on these colorful maps that there is water, hydrogen all over the place. It's concentrated on the poles and weaker on the lower latitudes, and this leads to the assumption that this is ice, subsurface ice buried under a small layer of drier regolithlates. The fact that ice exists only where, let's say, it's cold enough to be so, is supported by the fact that it exists more on poles. Mars' rotational axis is tilted like Earth's, which leads to seasons, winter and summer, and with that, although Mars is much colder, so instead of having snow, water snow, on Mars there is CO2 snow. So it's so cold that CO2 actually freezes and falls mainly on the poles and creates polar caps that extend on the North Pole down to 60-degree latitudes, on the South Pole up to the 50-degree latitude. So in order to choose a mining site, these regions were excluded, and I concentrated on regions that stayed dry ice free during the whole year, let's say. The subsurface ice content was modeled with this two-layer model and calibrated with ground truth provided by landers. And I propose 2 mining sites in the equatorial region, the Arabian and Arabia site, which are thought to contain 15% of weight percentages of water, and 1 just outside of the reach of these and 1 just outside of the reach of the dry ice caps here in the mid-latitudes. In the equatorial latitude, there is a problem with this map. Basically, it's not sure that this is actually ice, because the climate is too warm in the equatorial region to actually have stable ice underground. So maybe this is hydrated minerals, or it's remnant ice from a recent change in the Martian climate. This is basically a mystery, and if we want to choose a mining site in the equatorial region, this certainly will need to be made sure that this is actually ice before we sense it. Now the mining system that I worked on was this Martian Situ water extractor presented in Zakni's paper. And what I did was taking this concept and put it into context of a mining site and surround it with subsystems and logistics that it would need to work. The way it works is that it has an auger drill that drills down to this ice-rich layer, and once it's drilled down, it's retracted, retaining the icy soil. It drives a bit further and pulls down a sleeve, loads it against soil and to seal it, and then there is heat injected into the auger, and with that the ice into the soil condenses, melts and vaporizes, and is then bled through a valve and condensed and collected. This part of the system has been tested by Zakni, and it works. Once the water is extracted, the drill is exposed again, turned in order to lose the dry soil, and it's ready for the next operation. During these tests, it came up that the energy need for 1 gram of water was of 1 watt-hour. So in order to mine the 30 liters per day I mentioned earlier, over a year this represents 30 tons. And with this, let's say, energy weight efficiency, we see that we need 11 megawatt hours just to mine sufficient water with this method. The first subsystem, and the most important, is the mining subsystem, consistent of the auger drill and this leaf in order to create this mining chamber in order to extract the water. So the number I told you before, 11 tons per year, if we condense it into an hourly mining rate, we need 1.9 kilograms per hour, and we can, using the definition of the mining rate, we can link the volume to the water weight percentages. So this dependence is shown on this graph, and we can see that for the mining rate, the proposed, the rootless site, which has 40 water weight percent, the volume of the mining chamber needs to be 3.6 decimeters cube. And Then the next task was to size the drill actually, and the driving requirement I used was to minimize energy consumption. And this turned to happen when the radius was augmented, because basically the height retracted, the time for the drilling is lower, and with that the energy is lower. However, with a growing radius the power increases, and basically it's limited by available power, which I, let's say, put the limit at 2 kilowatts, and this leads to 50 watt hours of energy consumption for one drilling operation. The next very important subsystem is the electronical power system, so how to provide power to all subsystems in the rover. And the popular method to do so is through solar panels. And in order to know how much energy is available on Mars' surface, I modeled first the energy on top of Mars atmosphere. Sorry. Then I estimated the transmission through the atmosphere, and multiplying these two vectors gives the energy available on the surface. So we can see the energy through a year with summer and winter. This is mainly due to the day length, and then further the transmission again depends on not again, but it depends on the optical depth. This is a parameter that contains mainly the dustiness of the atmosphere. So it's high when there is a lot of dust, which, for example, happens through dust storms, which can encircle the whole planet on Mars, and low on clear days. And secondly, on how high the sun stands, because when the sun is low, the light has to travel through a lot of atmosphere and has more chances to be scattered. So we can see again in the winter there is not a lot of light transmitted, and in the summer there is a lot. I averaged this transmission and plotted it over a whole year, and multiplying these two gives the energy that's available through the year on the Mars surface. And what we can see is that on that mining site I proposed, there is over 100 days without basically solar energy. So we need to size the battery that energy collected in the summer can be used in the winter, which grows again the mass requirement because batteries are heavy. So through a year we have 620 kilowatt hours per square meter at this position, and in order to reach these 11 megawatt hours I mentioned earlier, we need 180 square meters of solar panels. And this obviously cannot be carried around by a rover, so we need maybe a loading station with solar panels, and the rover can go and charge during the night and mine during the day. The second option would be a radioisotope thermoelectric generator, short RTG. This is basically radioactive material that slowly decays and gives off heat in the process, and temperature difference is then used to create electricity with so-called thermocouples. This is a very inefficient process, so of the thermal energy that is at this position, there's only about 7% of energy converted into electrical energy. Another, say, version of this device is the ISRG, the Advanced Stirling Radio Isotope Generator, which uses a different process of converting thermal energy into electrical energy, which is much more efficient. But it's under development, and this development has even been stopped. I compared the three methods for energy, for, let's say, providing energy, and based on these criteria with those weights. And as I said earlier, weight is very important because it costs a lot. Reliability obviously is also very important because once you send something to Mars, you can go there and repair, which is a bit different when there is a colony, but still reliability is very important. And Well, I can go into detail if somebody is interested, but for time I will move on and say that the RTG scores best, mainly because we can use the thermal energy directly, where basically to mine and heat the icy soil contained in the auger, we need thermal energy. And what we would do with solar arrays is take the solar energy, convert it into electricity, and then into heat. While as here, we just take the heat and transfer it. This is much more efficient, and with that, much lighter for the same energy. There is, though, an issue with RTGs because of planetary protection. So there is, how to say, this would need to be looked at closely because RTGs, obviously, it's radioactive, so it's radiating, and you can't put that anywhere on Mars. Well, you have to, how to say, look at it. Yeah, so the RTG was chosen, and so the RTG gives 160 watt of electrical energy, beginning of life, and as we saw earlier, we need 2 kilowatts of power for the drill, and so basically the RTG can't directly give the power that the drill needs, so we need batteries that store energy and give off high power, but during short time. Here you can see the typical breakdown of a mining operation, so the process I mentioned earlier, and we can see that the drill here consumes the most energy, even though it's very short, only 1.5 minutes. And the size of the battery was chosen to be 500 watt hours, and for example, if the RTG would fail, it could drive with full batteries for 850 meters. The next very important subsystem is the thermal control system. Important here because, as I said, the heat of the RTG would be used to mine, actually. So it needs to transport large amounts of heat from the RTG to the auger. The way I propose to do is using phase change materials. So this is basically loops of tubes which are filled with a liquid that can change its phase change materials. Changing its phase, it gives off and takes large amounts of energy. So when it vaporizes, it stores energy, let's say, and it will be conducted to a colder part of the rover, namely here the auger, and condensed there, losing its heat. This kind of thermal control system is used also in combination with RTGs, for example on Curiosity, but the fact to use the heat of the RTG to mine is new, so this is something that has very low technical maturity and would need to be investigated first. Like the next step would be to simulate this and then maybe test it with an experimental setting. The rest of the rover is basically standard, let's say standard. You can talk about standard, but the rover weighs about the same as the Mars exploration rovers, Spirit and Opportunity. As shown in the mass budget, we can see at the end there is 250 kilograms, which is in the same region as these rovers, so we can adapt fairly easily the mobility system, so the wheels and the suspensions, as well as the mechanical structure of the rover to contain all the rest, along with communication systems and the intelligence the computer could be used as well. I took margins depending on how mature the technology is, so what we talked about earlier, the mining subsystem, for example, is new, so we need to have a big margin to, how to say, absorb this uncertainty. And stuff that is used on the already on Mars with the Mars exploration rovers, for example, the structures has lower margins because it's already used. We can see here also the top speed of the Mars exploration rovers is of 4.6 centimeters per second. Now, alone, the rover can't exist. Let's say he needs infrastructure around. If the rover mines at the Rupa site, which was roughly on the 60-degree latitude, the distance between the colony and the miner, because the colony is estimated to be on the equator because the solar energy disposition is highest there, and the colony is thought to use solar energy to provide its powers. The distance between those two would be of 3,600 kilometers. And if the rover roves there, it takes him 2.5 years. So this basically is not possible. So a high speed and long range transportation system is needed. The problem is that that doesn't exist at all. So this is another point that has very low maturity and has to be looked at sooner rather than later. If we estimate this transportation system to weight 750 kilograms, we get weight mining efficiency. So this is basically the production rate divided by the weight of the whole mining system. We get this efficiency of 11 kilograms per year per kilogram. And there is a second strategy that we can choose is to mine close to the colony. The problem being that we don't know if the hydrogen there is actually water ice. So this would need to be investigated. And also, if basically the lower percentages of weight water percentage in the equatorial region is plagued by larger relative uncertainties because the signal that the gamma ray spectrometer on Odyssey gets is weaker. So also it's not clear if there is actually hydrogen because uncertainty on these measurements was quite large. With 2 rovers, however, and the estimated water weight percentage, the mining rate of 30 liters per day could be reached. And since the rovers would be in proximity of the colony, they could just rove back and no transportation system is needed, which would lead to the efficiency of mining mass per year of 23 kilograms per year per kilogram, which is better also. Another infrastructure that is needed are storage systems, and there we need to find a way also to transfer the weight from the rover into the storage, which could be a tank, for example. I mentioned most of the technology gaps already, saying that technology that is used from the Mars exploration rovers has very high TRL, which is because it's already on Mars and used, and the systems that yet have to be developed or even tested to work have very low technical maturity. So what we need is transportation systems and test if this RTG heat used for mining actually works. So to conclude, the water requirement for a crew of 4 was estimated to be 30 liters a day. Water is thought to be widespread underground of different water weight percentage and in different depths buried underground. A mining site was proposed which contains 40 weight percentages, and basically the mining system was proposed, and if this technology works with the RTG heat used to mine, it would be a very mass efficient way of mining. The main technology gaps I mentioned was the transport system and exactly this way of mining using an RTG. Thank you very much for your attention. I'm looking for questions now and like to finish on a bit less serious now.
Yeah, I have a couple of questions. Okay, so how do you get around the problem of not knowing what your hydrogen is?
One way is...
Actually, I thought on one of your earlier slides you said that the hypothesis that it's water has been largely confirmed by
ground truth.
Yeah, by ground truth. But how do you confirm?
Okay, so basically there is this map with quite big, depending on how strong the signal is, uncertainty. And based on that, they made a model calibrated on the ground truth they had at this position then. For example, now Curiosity is here, and Curiosity has the same gamma ray spectrometer and measures water weight percentages. The highest it measures was 5.5%, whereas here we're in the green region. We should have between 9 and 10, 11%. So let's say this is far from certain. And one way is exactly you pick a potential mining site, you send an exploration rover there, and you look at how to set the measurement, which were from very close range, are of much lower uncertainty. So this is a way. Again, another mean would be to have this mid-range, for example, aerial mean of traveling with this measurement, with this spectrometer, so a glider or a balloon or something.
Part of the problem with that spectrometer, and using that spectrometer over and over, is that it just detects hydrogen, right? It doesn't necessarily detect water.
Yeah. Now, in regions where the ice is predicted to be stable, it was actually found. Now, another way of confirming this is these meteorite impacts. So basically, when a meteorite impacts the soil, it shows what's beneath the surface, and it shows icy structure that slowly fades away with the speed that is expected from water ice, knowing the composition of the atmosphere and the thermal environment. But again, these are strong indications, but not proofs. So the only way is actually to go there, drill.
One thing you didn't explain, which I know is in the report, so I've seen the picture, but what are you doing all this drilling for ice for? Why don't you just go and scoop water up out of a lake?
Well, there is no liquid water on Mars because the atmosphere is so thin. So every say form of water that gets close to the surface is immediately sublimated into the atmosphere.
So there's only really two phases of water.
Yeah.
Yeah, you could have shown that picture in the presentation. Okay, any other questions?
Yeah, I was wondering if you considered water recycling within the colony and what effect that might have on the rate of water that you needed to extract.
Sorry, I didn't get
the
question.
So there's a potential for recycling water inside the colony?
What as assumed in the water requirement of 30 liters per day is the recycling that is used on the ISS, which has an efficiency of 75%. The problem is that most water is used for growing food, something like 90%. And basically there the water goes into the plant actually, so this water is lost, which you can't recycle.
We need to back out of the plant later. So the plant would retain some and some of them would be expired.
Well, you get back some from the plant. Another form you get is back is in form of oxygen. Basically, the plants growing, they produce oxygen, which creates an excess actually of oxygen, which is an issue because if you don't separate the plant and the living space, you get very high oxygen levels, which is dangerous because a lot of oxygen is a flammable environment. So you need a system that actually stores the oxygen in a fire-safe place. Certainly another question.
Yeah. So you talk about the drilling, and you say that 1.5 minutes takes to drill for 15 centimeters. So this assumption based on the ice strength, or
this is
assumption?
based on a drilling test that the same authors actually made in permafrost in the Arctic, and he reported a drill of 15 centimeters of diameter with a 1.3 kilowatt motor to drill for 10 centimeters per minute. And I scaled that drill I proposed for the mining system on that test. So I scale power to linearly to the radius, and I keep I keep the same drilling speed.
All right. What about the maintenance? Things go wrong in mine operation.
Maintenance. So at least in let's say the case of the miner being far away, the drill would need to be designed that things that can go wrong need either to be detected and avoided, or having the system being that strong that basically it can't break. On the other hand, if the rover is close to the colony, there is a certain amount of maintenance that can be done by the astronauts in the colony, but again, this should be minimized in order to minimize the, let's say, because it's very complicated to go out actually to Mars, and if something breaks, the rover can't actually, well, depending on what breaks, the rover can't drive back to the colony. So the design would have to be very, let's say, it would need to be stronger, or, well, he need to be robust enough to deal with everything that is expected to happen to him.
Similar to curiosity. Right?
Exactly.
So how about the risks? You know, I don't think you mentioned in your thesis about risks, but you know, having an operation in poles compared to equator region because of extreme environment,
Exactly.
might
Yeah.
exposed to more risks.
The main reason I avoided the polar region is the growth and retraction of the polar ice caps, which in every winter grow down to 60-degree latitude and can be as high as 2 meters. And to mine in that environment is much more difficult. Basically, I think the weight that you would need to carry to protect the mining system from that frost, or to every day free it from all that ice, would be much greater than basically the benefit of having more weight percentage is lost by all that infrastructure you put around. And as we see here, actually, you don't need much more volume once you are above this 30–40% water in the ground.
And plus, we'll be close to the colony, right?
Yeah.
The possible colony will be
You'll
in that area.
further when you go to the poles.
My last question is about, this is the water ice. How about, you know, you said that carbon dioxide ice. Is it anyhow could be useful to use as well?
Possibly, I don't know, but the carbon dioxide is abundant in the Martian atmosphere, 96%, I think, so it would be easier, I guess, to capture it under gaseous form than to have it under ice. There was a question behind.
Yeah, how deep would you have to drill, potentially? Or, okay, maybe be smart to say, how deep could this rover potentially drill?
Okay, so one thing is that you need to reach actually the ice-rich part of the soil. This skin of dry regolith is, how to say, varies between locations. What I used again to scale the drill was the ways that if I reduce height, I keep the same volume, but I reduce energy consumption, which is why the drill I propose is very short. But potentially I don't think there is really a limit besides actual stability of something long and thin breaks at some point. So I think it would be limited mechanically by the stability of the long and thin rod. But even for that there is solutions, because I mean, there is very deep drilling operations that happen on Earth as well. But the actual needed depth of drill is go below the dry part of the soil, and then once you're in the wet or icy one, you're limited by, again, I scaled it to energy consumption, so you want to minimize energy consumption, so you want to have as flat drill as possible, so not that deep.
So is the ice quality similar in every regions in the Arabia side, say?
Again, there is no information for that, so all we know is with large uncertainties how much hydrogen is thought to be around there. But again, this could be hydrated minerals, so really before I think a lot of money is put into that project, it needs to be verified that this is subsurface ice and that it's mined.
So what engineering skills you used?
I used, so this is called system engineering, where you basically you take a whole system, you look at each subsystem, and all these subsystems interact with one another. If one changes, another one has to change as well. So space system engineering is one skill, I'd say. I used MATLAB to, well, all the these relations I visualized with MATLAB here as well. Trade-off studies is a way of taking decisions into, well, any engineering project, weighted criteria to compare solutions.
So how did you decide the weighted criteria, either 3 or 2 or 4?
This is relative, let's say, between, you look at each criteria and you look how much importance each has against another. And so basically 5 is very important, 4 important, 3 is, let's say, average.
But
not important.
it could be small change based on the assumptions in it. It could be 3 or 4.
Yeah.
So this may, because 30, 130 and 116 are quite close to it.
It's quite close. It's just a way of, instead just saying, I take this because the energy is a bit bigger, you actually show what you base your decision on. All these tables have to be accompanied by a text explaining why you pick this important and why you give that score. For example, why I say 5 for reliability for solar arrays, not 4. And this is basically gives a roadmap of your decision and makes it possible to understand your decision.
Any cost as a criteria? Which one is more expensive?
Cost is hidden if you want in weight, and another cost, well, basically costs in space missions are dominated by
Weight.
launching and bringing it there, which is weight, and the second one is the development of the technology you actually bring. So this is TRL, technological readiness level, maturity, and weight.
Too many questions. I can ask them more.
All right, you've exhausted the questions. Thanks very much, Thierry.